What do suspension bridges, computer networks, and continuous topological spaces have in common? They all map the relationships between points and the paths that connect them. While these networks look discrete, redefining them through abstract topology reveals a deep symmetry that allows us to solve complex algebraic problems using purely spatial logic. Standard graph theory is combinatorial. It treats a graph as discrete data, a list of abstract nodes and their relations. Topological graph theory changes the perspective entirely. It treats the graph as a continuous geometric structure that can be bent, stretched, and rigorously analyzed using the tools of spatial mathematics. To build this continuous structure, we start with a baseline definition, the arc. An arc is a topological space that maps perfectly to the closed unit interval from 0 to 1. It has two explicit endpoints, corresponding to 0 and 1, and an open interior containing everything in between. Redefining a line as a space allows us to apply the machinery of the fundamental group, a tool that treats paths as algebraic elements. This rigorous groundwork is the required first step for the group theory applications we'll see later. With the arc defined, we can build a linear graph. A linear graph is a space written as a union of these arcs. But there is a strict rule. The intersection of any two arcs must either be completely empty or consist of exactly one single common endpoint. They cannot cross anywhere in their interiors. This brings us to a specific friction point for infinite graphs, the coherent topology condition. For an infinite graph, a subset of the graph is only considered closed if its intersection with each individual edge is closed. It has to be verified edge by edge across the entire structure. This chart from Munkres shows exactly how strict these definitions are. Look at figure 83.1. The wedge of circles. A full circle loops back on itself, so it is not homeomorphic to the straight interval 0, 1. To make this a formal linear graph, each circle must be subdivided into 3 distinct edges and 3 vertices. Moving down the page to figure 83.2, we see another example. Here, an infinite set of independent intervals has all their 0 points collapsed into a single shared origin point, creating a quotient space of mediating spokes that still obeys the rules of a linear graph. Let's test this logic. Looking at this figure 8 space, how would you construct it as a linear graph? Pause the video and calculate the minimum number of arcs and vertices needed. Recall the rule. Arcs can only intersect at their endpoints, and an arc cannot intersect itself. Because the loops connect at the center point, you have to break each single loop into at least 3 distinct arcs to avoid a self-intersecting boundary. The coherent topology rule and these subdivision constraints require extra work up front. However, this exact rigidity is the mechanism that forces even an infinite, chaotic collection of lines to behave like a predictable, one-dimensional topological space. Because of that predictable behavior, we get a cascade of useful topological properties. Looking at the text of Lemma 83.3, Munkres proves that every linear graph is locally path-connected and semi-locally simply connected. These specific properties matter for a very precise reason. In topology, being locally path-connected and semi-locally simply connected are the exact necessary prerequisites guaranteeing that covering spaces for this graph actually exist. This sets up theorem 83.4, shown here. It states that if you have a covering map over a linear graph, the resulting covering space is itself a linear graph. The intuition for the proof stems straight from our baseline definition. The base space is built entirely out of arcs. Because an arc is simply connected, any path along an arc lifts cleanly and predictably to a corresponding arc in the covering space above it. Proving that the covering space of a graph is inherently a graph itself is the critical maneuver. We have constructed a reliable bridge, allowing us to take abstract algebraic covering problems and translate them directly into visual, geometric graph problems. Now we can apply this to group theory. Let's look at the diagrams at the bottom of this page. Here, Munkres defines a tree. A tree is a connected linear graph that contains no closed loops, or what the text calls closed reduced edge paths. The lack of closed loops means a tree's fundamental group is trivial. In any connected graph, we identify a maximal tree. Any edge not part of that tree effectively creates a loop, acting as a generator for the graph's fundamental group. This all culminates in theorem 85.1. If H is a subgroup of a free group F, then H is free. Proving this algebraically requires extremely difficult brute force calculations. First, we translate the algebra into geometry. A free group is represented topologically as the fundamental group of a wedge of circles. Each circle in that wedge acts as a generator for the group, a path that cannot be shrunk to a point. Topologically, a subgroup corresponds to a covering space. Since we've proven that any covering space of a graph is itself a graph, and we know that every connected graph has a fundamental group generated by its loops, that subgroup must also be a free group. The proof is sustained by the structure of the space itself. By rigorously defining simple lines and points as topological spaces, Munkres allows us to bypass brutal algebraic calculations using elegant geometry. If you found this helpful, like and subscribe for more deep dives into foundational math texts.